All right. So my name is Vivek Sharma. I'm a PM on what we call the data center team in Exchange. And one of the rare occasions that I do get to come out and talk openly in the public about what I work on and what the team works on, it's really hard to explain. What is this thing called data center? And so what I figured, instead of me spending a bunch of time explaining data center, I'm going to start off with a little video. This is not one of the official MEC videos. I got strict permission from LCA to be able to show this to you. So this is probably not going to get recorded either. But enjoy the video. This kind of gives you a little bit of a view of what we call data center. All right, so the point of data center, or what we call data center, is around running Exchange at super high scale. Now, we gave a talk at MEC, the last MEC 18 months ago, and we tried to be as open as we could about how we run what is likely to be the largest deployment of Exchange around the world. And these days, it's probably one of the largest email deployments in the world as well. Now, last time we got really, really good positive feedback. The feedback was extremely good. It was not a marketing session. This is not me trying to tell you and convince you to go to the cloud. This is not my purpose. The purpose of this session is really to help you understand how we run the service, to have you go through the process of figuring out if some of these technologies are applicable to you, but more importantly, to build some comfort around the fact that, yeah, there's a group of people out there that are building some of the most high-tech Exchange deployments, and to also solicit your feedback. The good news is, based on the positive feedback from last MEC, we're going to be a lot more open this time around. If you saw the building of this content, if you were to follow how we got to the spot, you had to negotiate with so many teams at Microsoft just to be able to show you some of the stuff I'm going to show you today. And some of those teams I said no to, that we wouldn't show their content, but we're going to show it anyway. Because you guys are awesome. And I don't see anybody else here, so it's OK. The bad news is, there's going to be some bad news. Now, I want to set expectations properly. A little bit of bad news. The bad news is, because I'm going to show you so much internal stuff, much of it is not going to be directly applicable to you in on-premises, as in you're not going to have the same tools or technology. I hope that's OK, because the pattern is likely still going to be applicable to you, but this exact technology won't be. And you'll understand why as we go through the talk. In the talk, you heard a lot about big data, machine learning, and some of these things are ephemeral concepts. In fact, I saw a tweet from, maybe it was even Tony Redmond, saying, hey, there's a whole bunch of TLAs here and tech terms, and nobody's actually explaining how it's done. Hopefully, you'll see after the session how it's done. There are some caveats. Again, because I had to negotiate with like 10 different teams to be able to go show you some of the stuff we use across Microsoft. I can't tell you about exact user numbers. I can't tell you about exact hardware partnerships, out of respect for our partner ecosystem, as well as out of respect for our competitors, our friendly competitors. So some of those details have been omitted, but that's OK, because you will still get some really, really important numbers out of this talk. OK, that being said, let's go talk about Exchange Online. A lot of you have been with us through this journey. When we first started out, around 7 years ago, we were what we call city scale. City scale is, you imagine an entire town or country, or town or city onboarding to the cloud. 100,000 to 1 million users, 250 servers or more. You're doing updates every year. You can run it using a traditional operational model, hands-on manual. Things get done. Issues can be fixed. You can go open troubleshooting tickets, call support. It gets done. This is where we started. And on-premises was a core. From there, fairly rapidly, within a year or two, we kind of got to this, what we call country scale. Imagine 10 million plus small country, not the US, not one of the bigger countries, just onboarding to the cloud. 2,000 plus machines, 5 to 6 times a year, you're updating the code or updating features. A lot of things have to be automated, but there's still human orchestration. The difference between fully automated and human orchestrated is, imagine that you can do machine reinstall fully automated. But you still have to have somebody deciding which machines, at what time, which stage, watching it. Did it fail? Did it succeed? That's human orchestrated. Issues often span teams or areas, so you kind of have to have a mixed model. You can have people dedicated to running the service, but you also need kind of people around to help you troubleshoot issues. And then we ended up tweaking the architecture. In fact, if you've been watching 2013, 2010, the difference between the two architectures, you've seen a lot of effort on the back end, the front end roles, to make it more data dense, as well as make it more lightweight for front ends. That all came as a result of learning at this country scale that we call it. But now, at 2014 MEC, we can say that we're at global scale. You saw in the video, and the video is about a year old, and already it's stale. All the numbers there are already stale. We're way past the numbers in that video. 100 million plus users around the world, dozens and dozens of data center locations. We're doing updates almost every week, whether they be for our internal optimizations for our service or they be for end user features. We are truly at this machine orchestrated and machine automated world where the machine is deciding what to go do. Machinery is deciding what to go do next. Humans are making the top-level decisions. Let's say roll out this build. But really, machines are making all the decisions on what to do next in the service. Our development team is our operations team. We work in this model called DevOps. Everyone fixes. Everyone's on the service. We can't afford to separate out the people who work on the service versus the people who fix code or write the code for the service. And architecture is really forward-looking, and you saw a glimpse of that from all the folks giving the keynote as well as all the sessions. So we're at global scale, as we like to call it at this point. The big realization for us is that everything changes at global scale. Turnkey software, I'll be the first to admit that we would love to go use some of the things that we ourselves have built at Microsoft, but at that enormous scale, even the stuff we've built at Microsoft cannot survive or last. And so what we have done is, and by we I mean lots of groups like Exchange, SharePoint team, and Office 365, we've built highly customized, purpose-driven automation. I'll show you some of that in the session today. We have specialists owning their piece of the puzzle end-to-end. So if you have somebody who writes the code for OA, they write the code for OA, they write the great features for OA, but they're also responsible for carrying the pager. When OA breaks, their code tells them. And if it's not automatically recovered, they have to pop on and fix the problem themselves. Huge problem or failure domains. And error rates, which were survivable at that city scale or smaller, is extremely hard to survive at very large scale. Even a 0.01% error rate at 1 billion transactions a day is a huge number. It is just unbelievable how big that is. And every single action we do has a consequence or a potentially dramatic consequence to our users. And this is kind of the dilemma. The bigger your user base is, the more demands you have from that user base to go have updates, to fix issues. And the more updates and changes you make in the service, the more opportunity there is for you to screw something up. And so we have to be very careful about the number of changes we make in the service, which are a lot, at the same time making them safely such that we don't break anything. So everything changes at global scale. The biggest realization we've had is, there's no sacred system that we have that hasn't broken yet or will not break. Every single thing that we have in our system, including the people, have broken at some point or other, and they have to be reinvented. The systems have to be reinvented. We have to create new processes. Some of the things that we'll talk about in the session will show you the evolution of that code base as we've grown the service as well. One of the best examples of this is, I look back in the slides I presented at the 2012 MEC, and we had, some 10-odd data centers listed here. And in fact, Microsoft has more data centers than what's listed here. We have lots of edge nodes, which are network connectivity sites. This is like the PR-approved slide, so I can't show you the full list. But even the difference between 2012 and 2014, I was amazed. Even working in the area day-to-day, I didn't realize that we had data centers in some of these locations. And this is like the most, this is the most weird realization when you think about what goes into building these data centers. It's physical buildings, land leases, it's data center capacity, energy efficient data centers, like all that stuff is happening in the background. So it's not just the software that's changing, the physical footprint of our deployments around the world is changing dramatically. The best illustration I can give you to that is this chart. What this chart shows you is our server deployment pace over the last year and a half. So 2012 MEC is somewhere I don't know when the last 2012 MEC was, around this time in 2012, I guess. But each one of these lines, and each one of these rows and lines represents a server being added every single day. So leftmost is in the past, rightmost is most recent. In fact, it's gone up to last week. If you notice, there hasn't really been a time in our service that we're not deploying servers. And this is adding new capacity. That's what this represents. The cool thing is, yeah, we're okay at adding new capacity. The kind of interesting news is, and we generated this chart for MEC, and we didn't realize this until we generated the chart, is that we think we might be hitting a hockey stick. That's what the red lines represent. Hockey stick represents a point in your service growth where you certainly start becoming nonlinear. The pattern that we've seen to date no longer applies. Now imagine if that continues. At that pace, we're deploying on the order of hundreds, 200s, 300s, maybe 1,000 servers a day, if that trend continues. So all the techniques we've used in the past at the city scale, at the country scale, no longer apply because you cannot apply. For example, in the city scale, we used to have a group of people just go do the server deployments. 10 people to do 100 server deployments. Now do the math. If 1,000 servers are being added every day, how many people will you require to be able to deploy? It's just not feasible. It's not cost effective. It's not possible to do because you'd be, one, burning those people out. But more importantly, I don't think we can ever scale doing the same way that we were doing things before. Here's another view. This is more from our service internal perspective. This is transaction growth. I'm not allowed to give you the user numbers, but I can give you something that is a good indicator of user growth. This is just the last 3 months. This is not going over years like the server picture was going over. Just the last 3 months. Now you look at 1/1/2014, beginning of the year. We were at 5 billion authentication requests being serviced by our Active Directories in the service. Fast forward 3 months, we're at 8 billion, 62% growth in the last 3 months. I don't know about you, but that scared the crap out of the team back home. And of course, we found a great bug. It turns out some of that growth was accidental. It was because we introduced some changes that increased the number of transactions. But the bottom line is the system still had to service those transactions. So if we didn't have the capacity built in, if we didn't have the infrastructure to go and handle that level of growth, we would have been hosed immediately. So the product and service has to handle spikes, whether they be accidental or from user growth. And of course, now we've kind of tapered off. We're back to maybe 5 billion transactions, but we don't think that this pattern is going to ever stop for us. So I hope you're getting the image of how much we've grown even in the last year and why the techniques that we've used in the past are no longer applicable. The biggest thing that we've done, and this is now honing in on what this whole data center concept is that we've kind of separated our world into 2 chunks. One is the core product itself, and this is the product that you deploy, you get the benefits of it. This is in the light gray. These are all the partitions that we run. It's very, very similar to what you run on premises. And this is like, the heart and soul of Exchange, the HA code, the CAS code, front ends, all that good stuff. And that stuff is being tuned and optimized, and you're getting it directly in your hands. But turns out that managing that much capacity on the ground requires some special code of its own. And that's what the blue layer has become. This is what we call our data center service fabric. This is the code that allows our engineers to work efficiently at massive scale using automation. Our automation built into 3 pillars. One, we are super, super data-driven. All the signals that we have in our system are collected, analyzed, and used to go describe and in some cases predict the next course of action and protect ourselves if things go wrong. The next big pillar for us is security. I know there was a security talk yesterday, so I'm not going to spend a ton of time on security here, but this is the stuff that allows our service to be compliant. It allows our service to be used by folks who require data residency and all kinds of controls. It also is the stuff that protects our service from the nefarious people in the world that want to crack in. The last piece is the automated piece, which is the changes, safety, repair, orchestration, all the stuff that allows us to scale without requiring millions of people to work against the service, or not millions, thousands of people, human operators, to work against the service. And even in these 3 pillars, there's a lot of stuff. It turns out that you require a lot of things to go build a service fabric. You require orchestration, which I described as the act of deciding what to do next, deployment and patching. There's, by the way, a great talk coming up tomorrow, which is all about making changes at high scale that I encourage everybody to attend. Monitoring, this everybody gets. Diagnostics and perf, so our engineers can figure out what's going on at any given time. Big data, streaming data and big data. On-call interfaces that allow engineers to log on and figure out what's the problem. Notification alerting, how do we find out if the system itself has detected a problem? Provisioning directory, which is what you saw, the transaction growth, the authentication growth, as well as just bringing users back into our system. Networking and new capacity. Capacity is just the growth that we require to be able to service all the users that are onboarded onto our service. This is a lot of stuff. And again, let's go back to the bad news. The bad news is the majority of this stuff is kind of handcrafted for just running Exchange Online. And a lot of people at this point are like, well, why are we having this talk? Well, we're having this talk because a lot of this stuff is still going to come down to on-premises, but it's not going to come down in the shape or form that you potentially might think. And the best way I can give you a demo of that is let's talk about some of the stuff that you saw in the keynote. In the keynote, and of course, like, the industry is full of terminology like this, right? So in the keynote, everybody's like, oh, big data, machine learning, big data, machine learning. But it's really hard. Like, I realized through the keynote that it was really hard to kind of get across the concept of what big data really means. And so, we tweaked I asked a few of the fellow engineers that are here, we tweaked the demo so that we could, and this is one of these tools that I had to get strict permission because nobody, I bet you nobody has seen this outside of Microsoft so far. This is showing you our Cosmos system. Cosmos is this technology which was built by the Bing team. And I'll walk through this. The Bing team, of course, recognizes that they are a data product first. They're going in, scanning the web, collecting a lot of data, going over a bunch of information on web pages and deciding what queries matter or not. That infrastructure, it turns out, is very, very handy for doing analysis of system-generated events, like log files. So what we have here is and as Exchange admins, you know these log files very well. Like, for example, the 80 driver logs. This is one of the most chatty logs that we have in the system, always used for troubleshooting. All these logs are being uploaded. And of course, these are again, system-generated logs. This is not user data. This is just the stuff that you consider to be the ancillary stuff on your servers. This is the stuff that says, oh, this event happened. This fault happened. All these logs are being collected from our servers, and what this report is showing you is the completion report. This is a completion of how much stuff is being uploaded at any given time. It's in percentiles because, well, of course, we want to see if we get as close to 100% complete or not. All the stuff is being uploaded from our servers. It's going from each one of our data centers into these Cosmos clusters. And you can go look at the list of log files and how complete they are. E14 CAS logs, 80 driver logs, but that's not like, the reason I'm showing you that is because it's comprehensive. The real interesting thing is what happens once it gets uploaded. Once it gets uploaded, it goes into these massive compute clusters, which are storage clusters, and which have lots of CPU cycles available to run techniques like MapReduce. These are the list of jobs that are running continuously, processing that data. And this is in the orders of, and these are compute hours. So this is in the order of, over the last 90 days, on the order of 6 or 7 million compute hours being used to go process those files. 7 million compute hours is a long time. But even more impressive than that is, I think, this. This is how much data. This is what we mean by big data. We have, for Office 365 all up, we have on the order of 37 petabytes of data that is being stored, out of 40 petabytes allocated to us. And over 90 days, it's grown by 10 petabytes as well. When people talk about, like, why can't we get this stuff on premises? Like, because nobody's going to have 37 petabytes worth of data on premises. That's why. It's not like we don't want to like share the stuff with you. It's just like, somebody raise your hand if you want to deploy 37 petabytes just for log analysis. All right. Okay, one guy. One guy. And I think that was a joke. So, 37 petabytes, like this is insane. And this is just one part of Microsoft doing work with this data. And this is not user data. This is not mailbox documents. Like, that's not the stuff that we're talking about. That stuff is kept in the, the sacred, sacrosanct, HA databases everywhere. This is totally separate. So like, at some point people are like, are you nuts? Why would you keep this data around for this long? And I'll show you why we kept this data around for this long. In fact, how do you think we computed that we had 5 billion transactions across our entire service? It was a job that took a bunch of compute hours against a bunch of log files which had stuff like, hey, X user attempted to access the service. Over billions of those entries. Imagine doing that computation. This is what the scale of the service is about. And if you notice, in the last 90 days, it's grown by 10 petabytes. I mean, like, that kind of growth is not possible to keep up with if you're doing a traditional box product. In fact, there's probably like only a handful of companies in the world can handle this kind of scale. And I'm not really sure if we can handle it yet either. Like, I don't know what the next step is, but so far we've been able to keep up with it because we were able to leverage techniques from Bing. It's not like the Exchange team built this stuff. We just use their stuff. In fact, a little joke. The Bing team was like, "Oh yeah, Exchange, don't worry about it. Yeah, we can onboard you. No big deal. It's nothing compared to the entire web." So they allocated 2 petabytes. Little known secret, they don't really check their allocation because we ate and we were like 15 petabytes. And suddenly they come back to us and they're like, hey, Bing queries are running slower because you're eating into our capacity. And so now we have 40 petabytes. All right, so does everybody kind of get like what I mean by big data now and large scale? That's what we mean. What I hope to do is, throughout this talk, I want to make sure that people understand, tie back all the concepts you heard in the keynote back to the way that we're running the service. And this is not to say that we don't ever think that folks on premises will benefit from this technology running in one place at Microsoft. Think of it this way. Why does everybody in the world need to go process the same log to get the same realization when we can do it in one place and we can just send the rule down? We're figuring out, using our machine learning or algorithms in advance, what patterns and correlations exist by crunching those 40 petabytes. And using that stuff, the decision that gets made, we can pump on premises. So you're getting the benefits of it. You just don't have to go deploy and do a bunch of the hard work around the compute and storage. That's a good relationship. So let's talk about data-driven. This is one of the pillars that I talked about earlier. The cool stuff about being data-driven is, data is one of these things. Like, you can geek out like Dr. Perry, you can draw charts, all that cool stuff. But the second thing is, the more importantly is you can get real insights, and you can turn those insights into real code, and you can make real benefits to your running service. And you get all this stuff, by the way, on premises as well. The stuff that you won't get on premises, built in automatically, I'll tell you what that is. But over the lifetime of the service, we've kind of find out that monitoring by itself is, it's kind of a weird game. It's kind of a weird game because traditionally people build monitoring with the idea that somebody has to take a look at the alert that goes off. And fundamentally, if you imagine the scale of errors we're seeing in the service, that's just not going to be a real option because we cannot throw enough people at looking at all the errors and alerts that are coming up. So what do we have to do? We have to go build systems that make the decision for you when the data comes together on what to do next. And so monitoring for us has evolved from being something which was detect to create an alert and have somebody take a look at it to being detect, analyze, and then recover automatically. And in the off cases that doesn't work is when we go engage the on-call person. So that's what this next section is going to talk about. We've built lots of technologies to go do this, but one of the primary technologies we have is something called the Insights Engine. It processes on the order of 100 to 500 million events an hour. This is, so the big data Cosmos stuff that I showed you earlier, that was kind of like long-lived data. Like, you decide after the fact, after collection, that something needs to be analyzed. And so you send a little compute job, and it's going to go run away for a while. And sometimes these compute jobs take a long time. You saw like 9 million compute hours. That's not instantaneous. In the running service, you got to make instant decisions. And so what we do is we take some of the realizations we get out of that compute job, and we figure out the correlations in advance, and then we process those correlations much, much faster to be able to realize the decision we need to make. So this engine, highly purposed. All it does is collect these events and then do some simple correlations on top of it. And it uses some streaming technology, which is very common in the industry. It's called like Trill, or actually, we can go over this stuff offline if you need to. Built on SQL Azure. And it's all custom code. But what this engine really does is it takes two majority types of event streams. One is active monitoring streams. Active monitoring is what we would consider, think of test cases or validation cases that you guys are running today on premises. Active monitoring is our scenario testing framework. We run on the order of 250 million test transactions across the world today. It's a pretty massive number. Think of that, each one of those being a scenario being tested like log into OA, open up a message. Or log in over EAS, open up a message. Think of that as being the scenario being tested. We do this approximately once every 5 minutes across a variety of different scenarios. And it's not like every 5 minutes there's a huge spike where we go authenticate. It's scattered out. What you get is near continuous checks. And the reason why I call it active monitoring is because it's a scenario-driven test framework. It's not like we're watching users log in and saying, oh, somebody's failing. No, we've written a bunch of test cases. And these test cases, they run in the cloud. They're not running inside the data center. This is another one of the big differences between on-premises and the service. They're running outside the cloud, testing our cloud. They're running from Azure instances. And of course, you have to have 2+ instances, because you can't just trust one instance to go check another instance, because what if that one instance that you're checking from is bad? So you need 2 to repudiate. That's what gets us these 250 million test transactions. Now, the cool thing about this is, it's not, the technology is great. Yeah, we can test ourselves from outside the network. Awesome. We have 250 million transactions. Awesome. But the most important thing is that because we're very structured in these tests, it allows us to create kind of a heartbeat, a very well-known heartbeat. These synthetic transactions describe the ideal state of the system at any given time. Now, I'll tell you why that's important as we continue the talk. This is one of the primary ways that we get alerted if something is wrong. And the reason why we can't really deploy this on-premise, imagine, like every on-premises customer out there, would they be willing to let us go, run synthetic transactions against every database in their system? I mean, maybe. You can give me feedback on it. We can talk about it. But imagine 10 or 15 million transactions coming your way from Azure instances worldwide. I'm sure somebody's going to just shut us down eventually. But for the services, it's critical. So the first one, active monitoring, creates that baseline, that heartbeat. Now, there's another valuable signal that exists in the world, which is the live traffic and the passive logs that it generates, or the error streams that it generates. So imagine, let's say that Comcast had an issue. And I'm just picking Comcast. I'm not saying Comcast is a bad provider. Comcast is awesome. Let's say Comcast has an issue in New York. And if somebody's here from Comcast, don't worry. Verizon also has issues once in a while. So let's say Comcast has an issue in New York. And the issue is that something changed on their end where the router is dropping packets. And the way that we see that on our side is we notice that there's spotty connectivity and eventually error signals coming from parts of New York. Those error signals can be matched then against the synthetic transactions we have, because the synthetic transactions tell us, hey, is the heartbeat, is the structured test that we're running all the time telling us that our service is okay? But if the passive stream, if the stream that is coming from our end users is saying, there's still a problem, now we can triangulate. We can say, oh, if our service endpoint is fine, but yet users are having problems, somewhere between our service and the end users must be the root cause, and usually is the network. So adding this signal on top of the baseline or the heartbeat allows us to figure out what's really wrong. So evolution of monitoring for us has become taking all these multiple signals that we have in the system and triangulating root cause based on the patterns we see in those signals. So on the right-hand side, what you see is what we call our red alert, which is as a combination function of all the things that we see happening from our synthetic transaction system, our active monitoring, or outside in. And you can see it's kind of dipping there. In the middle there, you see real OA traffic, a set of OA users in the world. It starts experiencing errors at the same time. And at the same time, we have data from our network, which says, oh, by the way, the network traffic itself has decreased during that time. Now, that's like a radically different view of monitoring than what we used to think about. In the old view of monitoring, it's like, OK, well, an alert got raised because an event fired on a server. I mean, this is radically different. This is, we're watching real traffic, real tests to figure out what went wrong and triangulating it. And because we have these multiple signals, and we have errors, and we have synthetic transactions, what we can do is we can identify the root scope or node where that problem occurred. Now, this is an example of an alert, a real alert. And this makes it very, very trivial for us to find out and go fix the problem. In this case, what happened is we noticed that the EWS component, this is one of our error streams for EWS. If you're a developer, you know EWS. The errors increased by 55%. And it turned out that all of those errors are coming from one particular server. And so what can we do at that point? We can just take the server, reboot it. We can move over to another server. We can fail it over. That's the level of granularity that we're able to get to because we can go triangulate across multiple streams. Right? So that's the evolution of monitoring for us. The next thing I want to talk to you about is, and again, this was in the keynote, so it was just like bugging me. It was like, we talked about big data. I hope I gave you a glimpse into big data and why exactly big data is big data. But the other thing that people talk about is machine learning. And it's like this buzzword in the industry, just like big data was. And people are like, oh, machine learning. Like, you attach machine learning at the end of everything, and suddenly you feel you're more awesome. So I got a little bit annoyed because at the end of the day, like, I want to quantify things. Like, I want you to understand what it really means. There are a variety of machine learning techniques in the world. And yes, there are some techniques of machine learning which are super complicated, like rocket science, I guess rocket computer science. But then there's the majority of machine learning techniques in the world are not, yes, not everybody's going to go do it, but it's not that difficult to understand. They are statistical models. Now, I'll help you visualize this. This helped me as well. I was super confused, so I had somebody walk me through this. For a while, I was just walking around being like, yeah, machine learning. But I finally got it. So what are we talking about here? Just like we talked about multiple signals, combining them, and suddenly you can start seeing patterns, and you can identify the patterns and triangulate using errors. Machine learning is not that different, at least in the rudimentary level. What's happening here is the light stuff in the background, that is the expected range. Now, assume in Cosmos, in this big data universe that we have, 37 petabytes, that much history tells us, if for example, let's say you took the transaction logs of Active Directory for your service, and you're watching it for a period of time, let's say 90 days, and you watch during the day, just like Dr. Perry drew, there's a curve, Monday to Thursday or whatever he said. Tuesday to Thursday is when everybody's working, right? Over time, you can watch these curves, and you can identify the expected ranges for that error stream or that log. Okay, that's what that light color represents. Now, if you have that rich history using Cosmos or some other big data system, and you've established the expected values, when you see the actual value of current data coming in, you can match the two up. And where they don't match, either too low or too high, you consider an anomaly. That's all it is. That's literally what the machine learning models are doing. It is a simple statistical model saying expected value versus actual value. And that's just standard deviation. So what we do is we watch our transaction logs for a variety of error streams. We calculate the expected value. And once we know the expected value, if anything goes beyond it or under it, we call it an anomaly. And that's machine learning in a nutshell for all the people. And now you can go back and you say, hey, I'll tell you about machine learning. This hopefully helped you feel like you can call bullshit on anybody who makes up machine learning at the end of any feature. But not to discount, there's actually lots of good machine learning stuff happening, which is a lot more complicated than this. at the end of it, this is kind of like the summary of the data stuff. What do you guys think this is on the right-hand side? Anybody have a guess? Heat map, that's good. Now, if that was a Microsoft person saying it, I'm not allowed. Server health. Okay. Another guess? It's close. So let's say that you had a compound function which described the active or synthetic transactions. You had your passive signals, the user signals, and you had, this, let's say, a model that says expected versus deviation value. Actually, you don't even need the last one. Let's just say you had the first two, and you're able to combine these functions to create a summary score. Just create a summary score. This is the view of all of our service across all of our capacity. Now, each column would be a day in a month. This is a month. Top to bottom is rows would be a capacity unit. It's not a server, it's a capacity unit. The colors would be any time we dip below 99.95 and between 99.5. And we have a pretty high bar. It's not like red is 50%. It's like 99.95. So all we're doing is we're calculating the compound function across all these different signals, and we're just mapping it to our capacity. Why is this important? Because you can very clearly see. Again, this is like the human intuition. You don't need machinery to tell you that this is important. Why? You can clearly see patterns where some capacity is just busted for a long period of time because you're in an incident or because there's some problems in our servers or whatever else. But we can use this knowledge to do something more interesting. We can use this knowledge. When we get an alert, we can map against this somebody said heat map, which is a great term for it. Against this heat map, we can figure out, hey, what went wrong and when? Because expected value dipped a certain percentage. So as soon as that alert is raised, we go do this calculation. And because we have really high confidence from all those signals, we can go ahead and tell customers right away. So one of the things we do in the service is, as soon as our compound functions, our data analysis, comes together and makes a decision that, hey, we're below 99.95, we go ahead and post immediately to customers saying, guess what? We think we might have an issue. This is really beneficial on two fronts. One is, one of the most annoying things in any service, including Exchange Online, including Netflix or any other service out there, Comcast, because that's my favorite one to pick on, I guess. If I'm going to get sued by somebody, it might as well just be one person. It's really annoying when you're experiencing a problem. You go to the support page, and what do you see? Service is running as expected. It's the most annoying thing in the world. We hate that. So we wired up all that great monitoring, all that detection. Before we tell our own engineers, we go and tell our customers that something is wrong. And of course, our engineers, it frees them up, right? Because they don't have to go worry about the active communication. They can just go worry about fixing the problem. And in the future, what we can do is, of course, get more and more granular. Because we have the root cause analysis, we can tell you, hey, by the way, this particular thing is the thing that got broken. Because one of the other requests we get from customers is, when things break, great, you're telling us, but tell me a little bit more about what happened. Are you going to make the same mistake again? Well, yeah, because we have all that data, we think we can go ahead and tell you, this server broke down, or this connection broke down, or this network is out. So that's a summary of machine learning, big data, signal analysis. And what I want to do next is I want to show you a very, very quick demo of some of this stuff in production. And production, actually, maybe is a too powerful word. I think the right way to think about it is dog food. This is our dog food environment. What I was calling earlier the red alert function, which is the combination of all our synthetics, is what I'm showing here. This is dog food, right? So nobody freak out and call your TAM to complain about the availability of the service. You can do that. Tell them to contact Jeff Teeper from the keynote. So the cool thing about this is, real time, we are seeing all the information as it's happening in the service against our environment. And of course, you see the red alert, the red line indicates there's a problem across multiple protocols. The protocols are hidden in the back there. And And this is our Docker environment, so this is not our real users. That's the reason why I'm showing you a Docker environment. But you can see what the impact is to which users in which capacity period. You can even go a little bit more in detail. We will let you go figure out what particular capacity unit might be broken at any given time, and we see what machines might be inactive or inactive. And as I was relating to you earlier, each one of the synthetic transactions is geared towards a particular scenario. So for example, you have OA, you have Outlook RPC, you have MAPI, mobile, EWS. All the things that we care about and test in the world is represented here. Each one of these scenarios is what's creating that synthetic heartbeat. And that synthetic heartbeat in a combination function becomes this guy here. And this becomes our experience indicator that you saw as the big green Christmas tree heat map. And of course, our engineers use this all the time to go navigate through all the capacity and see what the problems are. And most everything is looking good right now. All these things look a little bit scary. So each one of those failed transactions appears on here as a failure. The other thing we do is we test the front ends as well. So the way we discover the network is we are pinging the network constantly from outside our network, from Azure instances. So it allows us to, for example, triangulate down problems that we might be having just with our front end network. The other interesting thing we do is, and this is again, somehow I'm just going to get myself in trouble with Comcast. But this is our list of all the ISPs in the world that are connecting up to us, or that we're connecting through. And so what we've done is we've gone and figured out a way into seeing all the different connective points and peer relationships that we have with our ISPs. And we can identify, for example, in some cases, it looks like, hey, Beijing, APC North, China Unicom is having a problem, and it's 94% availability. This is a scenario I described earlier, which is like, hey, somebody in New York is having a problem. Well, how do we know? Well, we know because we have endpoints all around the world with the ISPs, the major ISPs. And if we notice that there's one of these indicators is dripping, we can go then figure out that ISP is the customers behind that ISP are having a problem with our service. The last thing I'll show is something that we call the error signals. Now, this page itself we're working on is still not as useful as we'd like it to be, but the detail page is actually pretty useful. The detail page is all the error signals that are coming in. Of course, you can slice and dice in many, many different ways. And we allow our engineers to go do that. For example, in this case, I've sliced it by failing component. If I click on it and I click on this guy, it brings up all the failures that we've seen in that time period. And the engineer gets all the rich details. And of course, I'm saying engineer because I'm showing you the visual usage tool. But really, machinery in the background is using all this analysis, doing all this analysis. So for example, here I can say, it turns out it was the OA mailbox error page. It turns out that the root exception is Microsoft Exchange Data Storage mailbox cross-site failover exception. So it's likely that a mailbox is failing over. That's why there's an intermittent error in OA. The other things we can do is, now going back to the details of the ISP, if I clicked on China Unicom, in fact, I did click on China Unicom, that's why this page came up. I can go down at the city level, and I can see in China Unicom what cities were the ones that are being impacted and why they're being impacted. In this case, it was Beijing that was noticing a problem. So this what allows us to go identify the specific set of customers in the world that might be experiencing a problem, even though our service is running well. And this last scenario is the error usage case scenario, which is all the errors in the world we are collecting in our service from our clients, and then we're able to triangulate down. So for example, in the last hour or so, we see a lot of RPC errors increasing from OA. Well, that might not be indicator by itself, but combined with the Beijing information, combined with the active information, combined with the network, we can probably reach the conclusion that we're having some sort of network issue that's causing RPC failures for particular customers in Beijing, which is a scenario I talked about earlier. Except I didn't mention China Unicom. I said Comcast. I really wish Comcast was having a problem now, because then I could show you. And maybe that's not the right thing to say. I don't know. OK, so let's go back to the slide deck. That was our data portion. And there's lots and lots of the folks that work on the service here I want you guys to go find us, talk to us about this, because we really do love talking about all the things that we're doing on the service side and how we can transform to the on-prem, or if you have questions around what your service is doing when you're online. So let's talk about the action portion. The action portion is pretty interesting. We talked about data. We talked about how important data is to go making decisions in the service. A lot of people ask us this question. It's like, all right, great. Well, how do you do work in the service? Well, it turns out we don't really do work directly in the service. We do. There are still manual things that we do, and we're trying to get rid of those manual things all the time. But if you think about the scale of 100,000 machines, 100,000 machines, you can't possibly assign a group of people to go work against those 100,000 machines and expect that everything is going to be just roses. And I'm not saying that as like, humans are broken things that always fail. But actually, in our experience, humans are broken things that always fail. I'm saying that because the scale, think about like a person doing an 8-hour shift. All right? Doing an 8-hour shift, maybe they can get through 100 machines. Right? Next person signs on, takes the next 100 machines. Did something happen to the person who was doing the first 100 machines? Like, did they notice a failure pattern? Maybe they forgot to tell the other guy because the other guy started his shift after the first guy left. Like, was there any knowledge sharing? Like, there's all kinds of little problems that occur when you try to do things at mass scale with people. It's not the people's fault. It's just the act of having an entity that cannot do things 24/7 continuously that breaks things down. So what we've done is we've replaced the need for having a human being, and actually it's the same human being. We can't actually have the same human being doing all that work. We replaced that completely with this entity we call the central admin. And central implies there's only one, but it's really, it's branched out around the world. It's massively geo-distributed. This is kind of like our mini brain operating the service. This thing uses the data, it uses the inventory, it uses all those facets of the service available to us to go make decisions. And to go make decisions about what to go do next. This isn't the thing that we're using to go automate everything in the world. This is the thing we're triggering all the automation in the world. There's a big difference in that. And the difference is around orchestration. Orchestration is making the decision what to do next. Now, let's take a scenario. You have 100,000 machines. You have to roll a change out. Do you do it to all 100,000? Somebody just say the obvious. No. You don't do it to all 100,000. You don't even do it to 50,000. You don't even do it to 10,000. You start super, super small. And you take the information available after doing that first one to the second one, and after going bigger and bigger and bigger. So having that activity being orchestrated by humans is a little bit error-prone because that state over time across these large scales gets lost very, very easily. But this thing can keep track of that state. You can issue commands to it, and it will go do the right rollout for you while keeping up with the right data. So for example, if you were going from DAG1 to DAG2, DAG1 was successful, DAG2, you're ought to go on. But if DAG1 failed, you know that you shouldn't be continuing this activity. Well, this thing can make that decision based on the data and only do the work if it's applicable and if it's allowed to do so. Another thing people ask us is, all right, so you talk about workflows, you're talking about doing this work, well, how much work is really happening in the service? It turns out we do on the order of 50 million workflows in our service every single month. All actions can be mapped to these workflows. So think of these as being reboots, reinstalls. You can think of this as being log collection. 50 million of these things happening every single month in our system. And at that large number, the number of errors you have are, of course, astronomical. So in this case, for example, we have on the order of 11% errors. That's huge. Across 100,000 machines, 11%, that's a big number. So the system has to deal with the error cases as well without human intervention, because you can't just call people in the middle of the night to say, oh, wow, this workflow failed. Commission some work manually to go fix it. Because at 11%, nobody can keep up with that. The way we handle those errors actually is one of the simplest patterns. At this point, people are like, oh my God, how do you handle errors? We just retry it. Majority of the time, it just works. I'm not joking. Like retries are somehow, actually you guys know this better than I do. Sometimes just kicking the box works. And so we kick the box a lot, 11% of the time. let's talk about a very, very big and more complex workflow. The trivial things in the world are super easy to talk about. Like everybody can imagine, reinstall, reboots, yeah, get it. More complex workflow that we do is something we call new capacity. This is super interesting. Now, it's going to take me just a couple of minutes to explain this chart, but I love this chart. This speaks to so much complexity in our system today. This chart represents the end-to-end pipeline of what it takes to get a piece of hardware into our service. So think of the leftmost as being most in the past. Think of the rightmost being most recent. And each gradient being a type of activity. So the light gray, the dark gray, the green, the blue, light blue, the dark blue, yellows, and greens. Those are all the different types of activities, right? And you can kind of see a little bit about the different activities. Approval for us to deploy capacity, which means capacity analysis, a whole bunch of other stuff. The green is the hardware vendor sending us the gear, getting to our dock. The blue is from the dock getting constructed into a rack that we can use. The dark blue is making sure the rack is actually healthy, the hardware is healthy. The yellow is once the rack and the hardware is healthy, it gets handed over to our deployment team, where the deployment team then takes it and starts to deploy on it. And the green is after deployment is done, we test it out to see if it's actually good, right? So those are all the phases. As you can see, through the effort of automation from past most to most recent, again, left to right, all the work that the Exchange team did, all this action, workflow, all that stuff, data, all the stuff we did has shrunk the yellows and the greens a little bit. But the vast majority of new capacity still doesn't change because we're dealing with the physical world here. And the physical world is super complicated. Like, for example, let's say you have 2 racks that you require in one location, and one rack is delayed. Well, you can't bring the other rack up. And you got to track that state over time. And because you can't bring that other rack up, everything slows down. This is one of the hardest problems we have in our service, which is how to get capacity in reasonable time into our system as fast as possible. So this complex workflow, we automated that too. Except we can't do the automation for the hardware vendor part. Like I'm not gonna mention any names, but hardware vendors, like you have floods in Thailand, all disk shortages, like it makes your life terrible. Suddenly you can't deploy. But what we have been able to do is go and shrink the yellows and the greens. And end to end, there's amazing, brilliant people at Microsoft working on that larger pipeline. So using the complex workflow system we talked about, the CA system, we were being able to shrink it from months to days. And using the data platform, we make sure that every stage you walk through, for example, going from discovery, allocation, deployment, service readiness, and live, all those things are gate checked by all the data signals that you saw in our big data platform as well as our monitoring platform. So you're not allowed to go release things into production if it's not a guarantee that as soon as live customers get on there, they're not going to be successful and happy and healthy. But even after capacity is added, there's still a lot of work to be done. In fact, the more hardware you have, the more problems you have. I wish we could run our software without any hardware, but that's not possible, I've been told. There's not enough big data and machine learning to fix that problem. Of course, you would expect this pattern to happen in our service, which is data heavy, hard drives, controller errors, the obvious candidates for being super high magnitude in our service. Repair is not a trivial activity. Repair is very, very complicated. It's not as simple as just detecting the problem. You have to detect it, you have to triage it, you have to figure out if the hard drive failed, what hard drive failed, you have to ticket it. This is dealing with the physical world. Once you pull out a drive, you have an empty slot. Well, what's going in the empty slot? Who's figuring that out? Who's making that happen? You have to track completion. You have to reseed data back onto it, and then you have to bring it back into service. It's a super complicated set of states. Well, so we built a system for that too. I'm going to call it Repair Box because we're not inventive people. And if somebody has better acronyms or cool code names to use, I'd love you for it. So we built this central admin workflow that goes and scans the world. It detects all this hardware that's broken. It tracks the states. It opens the tickets. The people go and fix it in the data centers. When it gets back into the service, replacement gear, it goes in, recommissions the hardware, and everything's happy. But super complicated workflow. This is part of that 50 million that's happening every month. And of course, this doesn't just happen on hardware level either. Software needs repair as well. What we do for software is it's the same thing, except in this case, an engineer is commissioning the fix. So what engineers do is they go and ask the system to go take a fix and take it out worldwide. The engineers themselves aren't making the decision on which machines to go pick or not. The system is making that decision. What the engineers are doing is requesting the ability to go send something out worldwide. And the system itself will then go pick the right capacity. A server, make sure the server is healthy. 2 servers, an entire partition, 2 partition, and then worldwide, or whatever the rings are. There's a great deployment talk tomorrow that talks more about this. The cool part about this is some of the classic problems that you've probably encountered on premises become very, very painful, again, at this high scale. For example, 100,000 machines, you go and patch 100,000 machines. It turns out maybe 1,000 of those machines were offline because they were under hardware repair. Well, you just missed 1,000 machines in your patch. So as those machines come up, let's say it's a 0-day patch. Boy, that's a scary scenario. 100,000 machines, but 1,000 machines didn't get patched because of 0-day. Right? Well, you're not going to keep a track of that stuff all the time. People cannot keep track of those states. So what we did is we built this thing called persistent mode. So the system, because it has all this inventory, it knows all the states, can then see, as soon as a new machine comes up, oh, I see you. You're new. You didn't get the thing that everybody else got. So I'm going to apply this thing to you. These are the type of scenarios that we have been able to solve because of this end-to-end system on automation. And again, like the point I'm making here is that some of these problems, while they were not egregious problems in the city scale because we could always deal with it manually, they're impossible to solve. Nobody's going to keep track of 1,000 machines being in these weird states all the time. And the only way you're going to solve these problems is to bring all the data together, all the actions together, have one system to go do it, fully integrated end-to-end. There's no exceptions. The last thing I want to talk about in this section is network. Network, it's like as soon as I talk about network, in my mind I'm like, don't say Comcast, don't say Comcast. But I guess I said Comcast. This is it's just a very, very simple picture of one of our data centers, one of our endpoints. This is not representative of total traffic. It's a small, small slice of our total traffic. But that's the only way I was able to show this to you because I have to get permission on everything I can show. What this is showing you is total traffic coming from various parts of the country. So New York is the yellow, New Jersey is the green. You can figure it out by yourselves that, hey, by the way, this is on the East Coast. Not a surprise. The interesting thing about all this stuff is networking it's got to be like the bane of every service person's existence. It is the worst thing to go figure out and troubleshoot. Most of the time, it's not under your control. A couple of weeks ago, we had I've heard of cable cuts. We've had a lot of cable cuts. ISP, we saw a cable freeze. I've never heard of a cable freeze until, in 7 years working on this service, somewhere in, and I'm from Minnesota, so I can say this, somewhere in Minnesota-Wisconsin border, the cables actually froze. They didn't break, they just froze. And I didn't know. I was like, does cold slow down electrons? But, so we had to send somebody over there to warm up the cables. There's like a cable warming machine. So the things you learn when you run services. So it's like the worst type of errors. The only thing we can do on the Exchange side, by the way, is our network and below. So in our network and below, if we notice a problem with our network and below, we immediately fail over. Our data tells us this network device is a problem, we fail over, that we can take care of. But the reason why it's so annoying to work in the network space is so many of the things that are broken are not under your control. But the things that we have been able to do on our side, and I thought this is a good reference architecture for folks that want to take away the slide deck and implement. We got rid of a lot of shared, duplicated network devices, and we moved to a more of a dedicated network device design. Now, in the past, many groups at Microsoft used to share the same infrastructure. So you'd have, for example, this is a total made-up example, so don't take this as, oh my God, the Exchange team and the Bing team share one device. But let's say hypothetically we did. That's bad, because what if Bing was having a problem and did something to that device? Well, the Exchange customer would be impacted. That's not good. So moving to a dedicated design allows us to focus all of Exchange Online paying customers their own devices, and we can do whatever we need to go do to recover without worrying about anybody else. One of the big improvements we've made on this side. And moving the redundant devices just reduces complexity and failure modes. You don't have to have redundant devices when you can fail over, especially in the Exchange architecture. So if anybody wants to implement this, you can come talk to us. We'd love to. This is something we can share because it's not something that's proprietary or hardware related. All right, so I'm going to give you a very quick demo, give you a couple more insights into capacity management. This is a view of our inventory. This is a view of all of our servers in all the different states. Like you can see, like some of these states are installing Exchange. I'm going to click on one of these and see if it comes up. Yes, it does comes up. This is an example of change history. So remember what I said is like if all changes are going through one system, it allows us to be super consistent on those changes across multiple machines. But at the same time, it gives us a beautiful audit trail. This tells us all the different workflows that are running on those machines. In this case, and of course, it's kind of embarrassing because we have like a cleanup diagnostics directory workflow, which seems like a problem we should have solved in the core product. But anyway, so we have a cleanup diagnostics workflow that's running, and it's successful. Great, awesome. And you can actually go check RepairBox. Now, RepairBox is such a high-level activity, of going and scanning all this hardware and fixing the problems it finds. That we like to keep track of all the different changes that RepairBox has made to a machine. So in this case, for example, consistency check, monitor check. It turns out that it didn't really have any hardware problem. Oh, in fact, hyper-threading was probably disabled at one point. We needed to enable it because that's our standard config, so RepairBox fixed it. So we keep all this history inside of our system, particularly because it allows us to go back and do hysteresis. I don't know why it's asking me for those credentials, so I'm not going to give them right now live, so it's recorded. The other things that I can do here is I can go to things like new capacity, which is the example I showed you. Now, this is dog food. Dog food doesn't get expanded like everything else. So, you're not going to see. But anyway, all the states that we talked about, allocated, deploying, service readiness, live, are represented. Our engineers can go see that. And the machines in the background are doing all the work. The engineers are monitoring progress. We can see a view of all of our live capacity. We can see in what states they live in, all the CASs, ADs, are they in maintenance, what the versions are. Everything is available for our engineers to go investigate at any given time. And of course, we also manage a bunch of Azure instances, load balancers, and routers. I'm not going to click on those because there are particular hardware devices and IDs there, and I don't want to offend any of our partner hardware providers by saying which one we use or not. And you can do the same thing around build. We can tell you how many servers of what build exist in the system at any given time. So this is what we do to go manage our capacity end to end. And the interesting thing to take away here is once you do get everything into the same system, in the same inventory system, into the same change system, it unlocks some of these super powerful other scenarios, like auditing. Auditing has been one of the really painful things that happens in any Exchange deployment. How do you know what happened at what time? Well, because everything is done by the same thing, all the actions are taken from central admin, it gives us a rich history that we can track down in time. What happened to this server? Who unplugged it? Well, we know. Well, fine. We know that it was unplugged, not who unplugged it. So last little section we'll go back to is around putting it all together, making engineers responsible and responsive. I want to very briefly talk about, this is not supposed to be a slide that tells you our entire service philosophy, but this is a summation of it. This is the set of principles that we operate by. Engineering first, high emphasis on mean time to recovery, use of automation, to run the service wherever possible. We do direct escalation, and I'll give you a slide and a preview on what that means. And we have a very low tolerance for making the same mistake twice. In fact, this is one of those grievous sins in the group, which is, hey, let's say you did understand and fix the problem, this serious problem that happened. But the next time, if you allowed it to happen, boy, that's really embarrassing because it was in your power to do something about it. Right? And so having this kind of culture really makes us, quite disciplined, let's just say, about running the service. The reason we want the entire team engaged on this is because we don't want anybody to have an out in not having the expertise being applied to the service. So I gave you the example of an engineer in OWA. If they wrote the piece of code and that piece of code broke, it's not likely that somebody who doesn't understand that piece of code is going to be able to fix it. Well, how do you make it such that everybody in the service is responsible? The only outcome is if you make everybody responsible. So there's no exceptions in the service. There's absolutely no exceptions. PMs, I see Brian there. Brian, marketing's even on call, aren't they? Yes, right. Marketing is on call. Although I don't think we let them touch servers. If we do, we should probably stop that. So the conception you should think about being a direct accountable as being every single person, no exception, being on call all the time, ready to make customers happy. The DevOps model. A lot of questions on this. It's like hotly debated in the industry. Lots of people have anxiety about it. It's not like some huge philosophical big deal. Really, it's about scale. How many people can you apply towards a problem in what ways? At some point, manual work at 100,000 server plus, 100 million plus users, it just doesn't work. Whether you have engineers do it or you have operations people do it. The other thing that does matter is the ability to fix code. It turns out at that large scale, the majority of issues we get into are issues that exist in the product or are new issues in the product, are code bugs. That's not necessarily operational issues. Those issues we understand. How do you get operations people to go fix code bugs? It's not going to happen. And so having the engineers always available to go fix the code bugs is essential for us running the service. And for efficiency, we just kind of combine the two. Because if you have automated everything, well, you have taken care of the manual work, but you still haven't taken care of the code fix. We have not developed the technology yet that fixes bugs automatically. When we do, the engineers can go off on call. But there are consequences to this. The consequences are that, yes, it is a human toll. The chart on the right tells you, this is from September. I didn't pick the most recent data because it's worse than this. The chart on the right is from September. And from September, you can see there at many times, people have spent more than 50 plus hours during a week on call. That's a lot of time. This doesn't mean that everybody's on call every single time. In fact, in September, 176 people were uniquely on call. Our principle and our philosophy is that we are going to put every engineer on call once every quarter. So multiply 176 by 3. That's how many times somebody was on call throughout the year. I mean, this is kind of a painful world that people live in. The reason I'm showing you this is not to elicit pity. That's not the point. The point is the engineers, if they by exception do not have an out of the system, the only option they have is to engineer their way out of this. So if they hate being on call 50 plus hours, the only option you have is to write better code, is to write more code, is to automate. Yeah, and it's a little bit of a, you guys are chuckling because you know it's evil. Yes, it is a little bit evil, but it works. Otherwise, we wouldn't be here. In fact, a lot of people are like, hey, I want to go to MEC. Really? You don't have a session to present? Yeah, but I can get out of on call. That wasn't me. So we have lots of roles. On-call engineers, incident managers. We put our execs on call. And we have communication managers. Every single person, no exception, is on call. And of course, we have a rigorous incident management system developed around this. When you get paged, you know who to contact because it's in the mail. You know what the error is. You know who's the directory responsible individual for that incident. You know who to, or you know what number to call. We use conference calls and bridges to go get everybody connected. A big principle is to make sure that people can connect outside of work. So a lot of our work happens over conference calls. In the middle of the night, not everybody's going to drive over the 520 bridge to get to the Redmond campus. So this protocol really helps us under pressure. It helps us go organize. It helps us go figure out what the right thing to do is at the right time. And it makes it possible for customers to, hopefully get fixes in the right time as well. And the last thing I'll do is very, very briefly, I will show you, last thing before we wrap up, is to show you our escalations. That's the problem with having too many IE windows open. So, when engineers are engaging with the system, they get this escalation view. And of course, this is very scary looking, and people shouldn't walk out thinking, my God, things are breaking all over the place. Actually, you can say that because this is dog food, and dog food is meant to be a broken environment because that's where we can make all our mistakes, so we don't do them in production. But this in dog food, you can see this person has acknowledged this alert. They're part of this group's 911 team. This is the particular problem. These are the tenants that are impacted. These are all test tenants. This is how long the incident's been active. That's a long time. That's not good. 97 hours. Probably should have picked a better one. And so, of course, you can move this. You can move this incident to a different person if you wanted to. You can do all this stuff to go manage the escalation on demand. The other thing we allow is, and this is something that Security Talk hopefully also covered, right? Which is if engineers do need the access they can go and request access, and somebody outside of that engineer will then have to go approve that access. So they have everything kind of built in to allow them to be efficient at a moment's notice whenever an issue does arise. Okay? This is the team. This is the team that builds the service fabric. You know, when I was getting ready for the talk, I said, hey, let's make sure that people feel the love. So we went out and took group photos. This is not the whole Exchange team. There's a lot more people in Exchange doing a lot of wonderful work. This is all the folks that are doing the work that we talked about here. The networking guys, networking guys are hilarious. First of all, I couldn't find them. And I was like, oh, crap. It's like, really, the networking guys? When I did find them, I realized how, compared to all the other things that we have going on, they seem to be a smaller team for one of the biggest problems areas we have. So it was an inner realization to go back and hopefully, they're not personally going out and warming up the cable, so I guess it's okay. But the cool thing is that people there are really, really excited about talking about the stuff that we talked about here with you. They're not, unfortunately, not all available to come talk to you. But I wanted to convey that we deeply, deeply do care about the service, and we are really here about the customers. All the systems I've talked about are built not for our own gain. It's about doing things at high scale so that customers benefit. The big deal for us is that we think we're in a good virtuous cycle, continuously improving, making core Exchange better. Like all the stuff that I talked about around scaling Exchange, you get that in on-premises. The stuff that you don't get is like the 37 petabyte cluster. And if you desperately do want that, I guess we can talk about it. But I'm not sure if the cost economics will work out. And the core product, of course, because it's running at this 250 million transactions, that's a scarily big validation number. You should feel great about the work that's going on in the service because it does improve the core product. And if you're moving to the online service, great. You just saw how we run it. So hopefully that was a good overview. I do have a favor to ask. And of course, you can always mail me. You can find me on LinkedIn or always mail me. Well, I do have a favor to ask, and I hope I can get one of my my Microsoft colleagues. Because I asked the teams, I go take these group photos. They asked me in return. They said, hey, how do we know that customers actually care about the stuff we talked about? And we're going to fake it. Well, you might care, you might not care, but we're going to do this. And this is going to energize you guys for the next session, too. I do this usually in all my sessions at the beginning. I'm going to decide to do it at the end. What we're going to do is, for the next 3 or 4 seconds, all right? The next 3 or 4 seconds. You're gonna film this? Yes, you're going to film it. So we're going to say, hey, team back home, we love you. Yes? All right. So when I count down, I'm going to do 1, 2, 3, and I want people to say, you're going to record this, right? Don't mess this up. All right. I want you guys to be as loud as you can, just yell and scream. Okay? I want Redmond to hear this. Everybody ready? Yeah? Okay. On the count of 3. 1, 2, 3. We love you! All right, good. All right, that's good, that's good. Now you're just faking it. All right. Okay, that's the end of our session. There's a bunch of us who work on the service. We love your questions. We love your feedback. And we love you. Thank you.